So today is Patrick Pilarski part 2, and it should be quite interesting. You can see he's dressed in a particular way for the occasion. So Patrick, take it away.
Great. Well, okay, so I think most of you remember me from round 1. Was anyone not here last time I talked? You guys are all here? Okay, awesome. So we're going to keep going more or less where we left off, but today I'm going to talk more on the use of machine intelligence and machines in general for things like assistance, augmentation, and interfaces. So we're going to get right into this. So what are we going to get out of today? By the end of the day, I hope that you'll be able to define assistance and augmentation. Also, I'm hoping you'll be able to understand there's 3 main challenges to building a powerful interface that connects a human and a machine or a machine and another machine. And so in particular, we'll talk about increasing signals, decreasing signals, and matching signals. Don't worry about what those mean right now. We'll get into that in detail. I'm also hoping you'll be able to state why machine intelligence is very important to human-machine interaction. Settings like this kind of system right now that I'm wearing on me right now. All right? We're also going to then get more into the meat of it, similar to our last time together. We'll get more into the meat of what abilities we might hope that machine intelligence can facilitate. We're going to look at how machine intelligence can actually be used. So we'll look at some concrete examples. In this case, we'll look at 2 concrete examples of how machine intelligence can facilitate a human-machine interaction. And by the end, I'm hoping you'll be able to give some examples, concrete examples of how machine intelligence can support assistive and augmentative technology. So this is our goals. Everyone on track with those goals for today? Good. And did everyone get the supporting article that was sent around earlier? And the video? Anyone get a chance to take a boot at the video? Yeah? No? Okay, good. At least some have, and we'll talk through it then. Great. So the question I have for you then is, what do you want to achieve that you don't have the ability to achieve right now? This is one of the key questions when we look at assistive and augmentative technologies. Or rephrased, what do you want machines to do for you? Not to make us sound lazy or that we want to push all of our woes off on our machine counterparts, but what do we want machines to help us with, to support us with, or to allow us to do better? This is a key question in assistive and augmentative technologies. So just to motivate this, I'm actually going to tell you a story. So it's story time. And this particular story is the quest for a third arm. And you can see that I'm wearing a third arm, not a particularly powerful third arm or a strong third arm, but I'm still actually using a third arm right now. And what's nice here is that this arm's been in the making for a little while. So I used to be in a punk band. Back when I was in high school, I was in a punk rock band. I played guitar, I did vocals. We weren't particularly good, and we weren't particularly successful, but we did write our own songs. But one thing I always wanted when I was actually playing guitar and singing, I was like, you know, it'd be great to be able to play guitar and hold a microphone or hold a beer or something at the same time. Like, right, you know, you have to actually strum, you have to hold the neck and fret and things like this, but you can't hold something else. I'm like, you know, it'd be great if I had a third arm. So I got a bit older, maybe a bit wiser, we don't know, but I go through electrical engineering. You're thinking, you know, it'd be great if I could actually solder something and have another arm to hold a flashlight or work in a resistor or a capacitor or something, or another arm to help me do what I want to do, but do it better. And maybe even be able to type and drink tea at the same time. Although an even older and even wiser me thinks maybe it's important to take the time to actually pick up your teacup, take a sip, and put it down. But leaving that aside, this is essentially a goal that's been ongoing for some time. And so this year in our group, where I've actually started the process of building this with my students, we've started working towards building a third arm that could actually be used, could be worn like the one I'm wearing today, and could be used to help us facilitate some daily tasks, everyday tasks. And so we've used it to do all sorts of things. We've tried to pick up objects or complete a task with 3 hands at once. So it's something that's challenging, and by the end of this lecture, I think you'll see why it's challenging and some of the exciting possibilities that are enabled by this kind of question, or how would you control a third arm attached to your body? Just having one is one thing, but being able to use it like you'd use a natural limb and receive feedback like you'd receive from a natural limb is another story entirely. So before we move on, I'll just give you a little introduction to this system. So right now I'm using very simple interface to control the arm, move bits and bulbs at any given time. So I can wiggle its wrist, for instance. I can move its shoulder back and forth, its virtual shoulder. I can move the elbow up and down. So these are kind of like the joints in a biological limb, but slightly different. And just to be very simple and to be very clear, I'm actually controlling only 2 joints at a time. So I can move up and down and side to side. I can do both of those at the same time. But if I want to control another degree of freedom, I'll switch. I'll let myself control the wrist and the shoulder at the same time. So this is actually something that's common in artificial limbs. And so it's a neat case study. It's also a simple way to demonstrate this system. But it's also giving me feedback. So what you can't see, and you probably can't even hear, is what's happening from this sort of fifth element style sleeve. Now, a student of mine, Adam Parker, actually developed this over the summer, but this sleeve is, allowing me to control the robot arm. So right now, I'm using a very simple joystick. You could use muscle signals or direct brain recording signals or any number of signals to control this limb. To give you a simple, clear demo, just a joystick. But what's also happening in this sleeve is the arm is giving me feedback. So as I'm controlling it, it's actually using vibrotactile feedback, buzzers that are embedded in this elastic sleeve to tell me which joint I'm using and how I'm using it. So the idea here is that there's actually bidirectional communication. I'm talking to the system, telling it what I'd like to do, and it's talking back to me saying what it's doing and what it's thinking. So this is important. As we move towards assistive technologies, especially very complex assistive technologies, we need to have this bidirectional communication. We need to have a streamlined, fluid, and natural interface that connects the human and the intelligent machine counterpart. All right, so let's move on. It's review time. So I'm going to put the arm down out of the way here so it doesn't distract anyone, it doesn't make noise. And there we go. And so now, review time. I think you all remember some of the stuff from last week. Everyone, again, remembers machine intelligence from last week, I hope, or 2 weeks ago. Let's just quickly summarize. Machine intelligence revolves around maintaining and using knowledge. Essentially, it's all about knowledge. And in particular, we talked about 3 kinds of knowledge, or 3 ways of dealing with the world. One is representation, how you structure the information in the world around you. Prediction, which is forecasting, the thing we've wanted to do since the dawn of time. Predict the future, find out what's going to happen in 2 minutes, or next week, or next year. And control, the ability to change or actuate the world in some way. And to do all of this in a purposeful way, not just willy-nilly, but for some reason or for some goal, in a goal-directed way. I think we remember the strengths of machine intelligence, but I'm going to summarize them again as well. One is that it gives us, as I said, enhanced control over this wild, squishy, and woolly world. So as the world becomes more complex and changes in strange ways, machine intelligence allows us to gain more control over that kind of world. It allows us to anticipate, again, to forecast what's going to happen in some time in the future. And more generally, it gives us very powerful tools to solve very hard problems. So this is really about optimizing control of complex systems and also pulling out knowledge, pulling out information from very complex or again, wild, woolly, and squishy worlds. Okay, so where might we want to apply machine learning and machine intelligence? And specifically here, we're looking at learning. Because remember, as we talked about, learning, the ability for a machine to learn, gives it the ability to do 3 very important things. One is deal with the unknowns in the world. So we don't need to specify all the details for a machine in advance. It can actually deal with that uncertainty and build up knowledge over time. Another is dealing with complexity. So if the world is really wild, the world is crazy, the world is hard to understand, and we can't hand engineer a system. We can't, as clever engineers, clever scientists, or clever citizens, be able to design a solution to this. The machine can actually handle that complexity. The machine can actually take over some of that wrangling of the world. And finally, dealing with change. The ability of a system to adapt to a changing world when the problem that it was designed for is no longer the problem that it's trying to solve. Machine learning allows systems to adapt. So that's our background. Okay. We're going to move into new material. Human-machine interaction. So firstly, this is a really hard problem. If I want you to leave with one thing today, it's that to think that, human-machine interaction is something that has a number of strong challenges because it involves all those things we talked about on that last slide. It involves complexity, it involves uncertainty, and it involves change. The relationship between a human and an assistive machine involves all three of those things. We're going to look today specifically at two different cases. I said human-machine interaction, but today we're going to look at assistance. So essentially a machine and machine intelligence that helps support or restore some of the innate abilities, some of our natural abilities that we've acquired over time. And augmentation. So this isn't just replacing or restoring function, but going beyond, giving humans new functions, things they couldn't do before, things they may not even been able to imagine before. And finally, we're going to move forward into the glue that holds this all together, which is interfaces, or connecting complex systems. Okay, let's move into assistance. And so I'm going to give you a series of examples. Throughout this next series of slides, I'm going to give you a few concrete examples of assistance and augmentation. Okay, so we said that assistance is restoring or supporting innate or acquired abilities. Okay, so one example, the first example we'll look at is alleviating motor impairments. So what do I mean by that? Well, I mean that essentially you've lost some of the motor functions of your natural biological body. One key example is amputation. So if someone's lost a limb, either through injury or illness or even birth defects, there's often the case where you need to replace or restore that function, usually through the use of some kind of robotic device, prosthetics. Some of these are simply mechanical, they're body-powered prostheses, and some are electromechanical. It means they actually use power, they read signals from the body, they have some kind of control system. So we're talking specifically about electromechanical or powered prosthetic systems, robots attached to the body. And the example I'm going to give you here is restoring function. This is a gentleman, Zach Votter, who actually used that robot limb. So you actually see on the slide here, there's a robot limb. Oh, here's my laser pointer. So you can actually see he has a robot limb connected to his lower body. And he actually climbed all the flights of stairs at Chicago's Willis Tower using that bionic limb. Now this is from the folks at the Rehabilitation Institute of Chicago. And there's something very amazing going on here, something almost miraculous, in that they've essentially rewired the nerves in Zach's lower limb. So now when he thinks about flexing his ankle and moving his body, flexing his knee, his actual robot limb will move. So they've rewired it such that when he thinks about doing a function, the robot does the function he's thinking about. So this isn't using substitution. It's not doing what I'm doing right now, which is using a joystick to control an arm. In this case, this gentleman climbed a tower by thinking about walking up that tower, essentially doing what he would normally do with a biological limb, and the robot limb, to some degree, mirrored the effectiveness of that biological limb. That's pretty wild, and that's pretty amazing. And there's actually surgeons here and colleagues here that are doing the same kind of nerve rewiring surgeries. It's called targeted motor and sensory reinnervation. They're doing that right here in Edmonton. So we actually have a world lead center in doing these kind of surgeries and developing prostheses to work with these surgeries. So this is something really cool. So this was an example of restoring or supporting functions that have been lost. And this was powered prostheses. What's another kind of assistance? So another kind of assistance is a social assistance or a cognitive or mental assistance. I'm showing here an example from elder care and autism by Maya Matarik down at the USC Robotics Research Laboratory. And what Maya's shown is a whole field of socially assistive robotics. And these are robots that assist you in more of a social sense. So the example on the slide here is actually of a robot that is helping to coach someone through physiotherapy activities. And there's examples of other robots that are engaging with a human on more of a social context. So remember, the prosthetic was actually wired right to the body. It had electrodes attached to the body. It was connected directly to the body. It was a very, very immediate connection between the machine and the human. In the social sense, the interface or the interaction between the human and machine is modulated by normal social conventions. So in this case, the robot actually has to do some kind of real coaching. Maybe there's verbal interaction. There's some kind of body cues. So human-machine interaction doesn't just occur on a direct sense, for instance, like I'm doing right now with my system here. So that's important to remember. But let's move on to augmentation. So I think we're clear with assistance. This is a way of restoring or supporting functions that we already have. Augmentation is going beyond, extending our abilities, our physical, our mental, and our perceptual abilities to the point where we can do things we couldn't do before. Machines can help us do things that were not previously possible. There's a new synergy, a new unity between the human and machine that creates something more than its parts, and that's quite magical. So here I'm going to keep giving examples more on the medical side of things, and here we're extending innate or acquired human abilities in terms of perception. The first example is improved perception, and what we have here is an example from MIT's CSAIL laboratory looking at video magnification. So if those of you who saw the video that I sent around earlier today, is this particular video or a selection of videos from this group. And so what's happening here is they're actually using a computational way of accentuating visual features in an image such that they become more noticeable. They're easier to perceive by a human. So in this particular slide, they were looking at it for the diagnosis of or essentially for monitoring the vital signs of newborns. You don't want to, after a newborn is born, you don't want to go muck about with the baby, poke and prod it all the time, keep touching it. It'd be great if you could actually take its pulse and do all sorts of other diagnostic measures just by looking at it. So if you could actually take its pulse very easily just by looking at the baby. And so what they've done in this particular example is amplified the pulse of the baby. You can actually see the skin tone change, flush red and then empty out again as the baby's circulation system is working. So it's a way of taking the data in a data stream and pulling out and accentuating salient features so that just by looking you can see something you would normally have to find just by touching or feeling or measuring. Another example from the babies is this example. There in the video that I sent around, there were two examples. One was just the regular video stream where you saw the baby breathing normally in its crib. Parents, again, the example in the video is that parents usually think, well, I want to know if my baby's breathing. That's a pretty important thing for many parents, and usually they get quite worried, they have to check. But if you can accentuate motion, so not color, if you can accentuate motion now, then you can go about and actually just look, and with this accentuation, you can actually see the baby's chest moving up and down very, very dramatically or noticeably. You can accentuate color, motion, and other features in a visual stream. It stands to reason if you can do it in a visual stream, you can do it in terms of all other sensory streams. So this is one example of augmentation. You're taking a data stream, in this case a stream of information that would normally come into the human body, and you are allowing that human to see things in that data that weren't previously visible. Make the invisible visible. I think that's even a quote from their video. So I encourage you to, if you haven't seen it, go on, give the video a look. They also show motion in cranes. So you can actually see small motions that are accentuated to a very large degree, and several other examples. Okay, so let's look at one other example. Augmentation in the case of extending physical capacity. So we just talked about extending perceptual capacity, and now we're looking at actually extending the physical abilities of a person. And many of you have probably seen this system already. Who's seen this particular example, the hybrid assistive limb from Cyberdyne in Japan? Okay, good. This is made by Cyberdyne up in Tsukuba, Japan. And it's an exoskeleton. It's a system that can be attached or strapped onto a human body to extend or reinforce the physical capacity of that body, to allow essentially little old Japanese people to carry like 5 bags of rice in their arm, or in these examples, to do disaster recovery. So we have here an example of how Cyberdyne has modified one of their HAL suits to work in disaster recovery. So a person with full biosafety gear carrying large objects and very heavy objects. So essentially, we've now seen augmenting or extending perception, and also extending the physical carrying capacity of a human body. So there's other exoskeleton examples. Who's seen some of the other exoskeletons that are on the market right now? Maybe some by the U.S. military. We have soldiers carrying like 300-pound loads with their arms. Yeah, so there's many other examples where this kind of robotic system, machine system, can bend to extend physical capacity. And while we're on the subject of extending physical capacity, let's go back very tightly to the medical field and look at the Da Vinci surgery system. So here you have a system where the doctor can go in and perform minimally invasive surgery by moving these very precise and numerous robotic actuators to go inside, poke around, cut inside the human body. Now, right now, this is allowing them to have some kind of sensation of what's happening inside the body. It's also allowing them to make very, very precise, exact movements with their extended body, the machine-enabled body. Now, right now, you can control one or more of these degrees of freedom. Imagine you could actually control all of those robot limbs at the same time. Imagine your doctor was wired in more tightly, actually like right into their brain maybe, and they could actually control all those limbs at the same time and all the functions of all those limbs. That's taking it to the next level. That's not just trying to perform with a robot on a small scale the same motion you might make with your physical body and a physical scalpel. That's going into the realm of vastly extending and branching out your physical capacity into a body that's not very much like your own body. So this is an interesting concept as well. All right. So what's our key idea from this section? The key idea is that machines can help to restore, replace, and extend innate human abilities. All right, so that's your bullet point line for this particular part of our talk, and we're going to move on now to interfaces. So I said that all of these things, assistance, augmentation, the connection between a human and machine is mediated or modulated by the interface, by that glue that holds them together. And by glue, I don't mean physical glue, although there's sometimes physical glue as well, but instead I mean the computational, the informational glue, the information processing, large-scale information processing that connects the human and the machine. And this is really about connecting complex systems. I talk about this in the context of connecting a human and a machine, but this could also be about connecting humans and humans, machines and machines. Essentially, any situation where you have multiple complex systems that are interacting over some kind of shared interface. And there's 3 challenges we're going to look at today. Really, there's only one challenge, but I'm breaking it down into 3. And that's increasing or extending a signal space, decreasing or focusing a signal space, and the general case that really subsumes those two, which is matching signal spaces. So if there's signals coming to and from a human body and signals coming from a machine, how do you match up the signals in those 2 spaces so that they can seamlessly interface? And the first one we're going to look at is increasing or expanding a signal space. And so this is kind of like what I'm dealing with here. I'm just going to spark up my arm again here. There we go. Okay, so what you see here is I'm using a very limited control channel, a simple joystick, to control actually all 4. There's 4 degrees of freedom on this arm system. So I'm essentially trying to perform tasks with a complex arm, for instance, picking up a pen, moving the pen around, dropping the pen. So I'm doing complex tasks with a multi-degree of freedom arm system using only a simple input channel. So this is the case of taking a narrow bandwidth, a narrow channel from the human, and expanding it out to control 4 degrees of freedom, 20 degrees of freedom, all the degrees of freedom that could possibly be controlled in a robot limb. So let's see the simple example. The simplest example, and this is actually an example commonly used in commercial prostheses and assistive devices, is where you monitor 1 or 2 signals from the human body, and then you map that, as shown in the slide, you map that over an interface to control a single joint of the robotic system. I could probably task any one of you here with the challenge of writing a tiny piece of code or writing some kind of engineered procedure that would take 1 or 2 control channels from a human user, like 1 degree of freedom on this joystick, and turn it into the control of 1 degree of freedom on a robot. Essentially, it's 1-to-1. You move up, the arm moves up. You move down, the arm moves down. I think you could all probably design something like that. That's a pretty clear thing to do. But now let's say you still only have that 1 channel, but I'm asking you to control all the joints that are available on the robot system in question. Let's say my arm here, maybe that's all 4 joints. Okay? So this is no longer quite so easy. I think you could still do it, and you'd probably do something like this, or exactly what I'm doing right now with this device, which is take that 1 control channel and use it to sequentially control the different degrees of freedom, and then allow the user to switch. So right now I'm controlling the shoulder, now I'm controlling the elbow, I switch, I actually feel a vibration down here in my wrist, and now I'm controlling the wrist. So switching is a very simple way of toggling human control, limited human control, through many, many, many different degrees of freedom in an assistive system or a robotic system. So, and you can do that based on making some way of switching, and that can be designed in advance. But this is probably how you guys would go about solving this problem. But now let's say that we have something like, I don't know, 30 or 40 different control channels or different signal channels in that robotic or that assistive device. How would you go about designing that mapping? How would you go about designing a system that would take this single channel of information from the human and be able to control all of those different channels at the same time, simultaneously? That's a very hard problem. And that's a key example of increasing a signal space, going from a limited number of signals to a extreme or extremely challenging number of signals on an assistive or a machine system. Okay, is that clear? Everyone okay with that? Okay, good. So we're going to move on now to decreasing or focusing a signal space. You may think, why would we ever want to do that? This is kind of crazy. Why would you take if you have a rich amount of information, why would you want to focus this down to only control a single joint or a single degree of freedom? So this is the case here. We have essentially some kind of information from the human side of the interface. Let's say I put sensors all over my body. Imagine this current sleeve that I'm using is actually peppered with different electrodes that are sensing everything from my body, galvanic skin response, signals from my muscles, signals from my nerves even. So there's many cases where you could record a lot of data from a human body, but I may still want to be able to use it to control this. So now that we have a similar system, we have a similar problem. How do you make that mapping? You have a cornucopia of signals. You have the horn of plenty and it's spewing out data of all different kinds. How do you go about using those signals to be able to control a common robotic or assistive machine? Okay? So again, this may still sound crazy to you. So let's look at this. Let's actually look at direct brain interfacing. So you may wish to, take a little skill saw, drill open a part of the human brain, and stick electrodes right into the actual matter of the brain, or lay them on the surface of the brain, or, there's all sorts of different options where you could record signals from the brain, and lots of them too. I mean, you could make a little tiny chip with hundreds of electrodes. People have done this. People have implanted it. We'll see this later. But this is still a very hard problem. Let's say you do have a direct brain interface with all those electrodes. How do you make sense of all those signals? It's not like you know exactly, well, not without a lot of probing anyway, that this particular neuron is the neuron that's thinking about moving my elbow in just this particular way, or maybe moving my arm side to side. You need to take a large body of signals, a mass of data which you may not fully understand, be able to map that to the control of even 1 or 2 normal degrees of freedom. And this is the case faced by most people who have something like a direct brain interface and they're trying to control a robot device. So you're focusing the signals down. So is everyone clear on those two different approaches? One is extending your signal space and one is streamlining down your signal space. And there's good reasons that you might want to approach both of those problems. But they're a general case of matching signal spaces. This is really the general case. And that you have some kind of interface where you have some number of signals coming from the human side of the interface, and you want to map that to some arbitrary number of signals on the robot side of the interface. So I say, I have 100 electrodes and 3 skin sensors on the human body, and I want to move this to a 20 degree of freedom robot arm with all the related control signals. How do you make that link between the human and all the things you have available, and that robot and all the things you have available? Okay, good. And often, this interface is very, very dense. So you may be able to record many signals from the human body, and you may have a very powerful limb. We have robot limbs that are being developed in North America now, which have up to 30 degrees of freedom. They can actuate their fingers individually. They have the ability to sense pressure and temperature. They can move almost to the same degree as a biological limb system. So we have great robots. We have robot limbs that can do amazing things. And we're getting better and better sensors every day. The ability to record signals from the brain and the body and the nerves. Our abilities to sense are also increasing. We can slap electrodes all over a human body and record with compared to previous years, very little effort. So the key remaining challenge is how do you map all those sensors, all that information from the human body to the control channels of that awesome, amazing robot limb that almost works as well as your biological limb. And then how do you go backwards? How do you take all of that rich information from that robot limb, things like temperature and pressure and what it's feeling, where it is in space? How do you communicate these things? Kinesthesia, proprioception, the sense of touch and texture. How do you communicate that back to the human such that they can interpret it and use it in a natural and intuitive way? So right now when I'm switching, I'm getting vibrational feedback about what the arm is doing. This is a very primitive example of going back the other direction. We'd like for the system to be able to actually feel what I feel. I tap it on the desk, I should be able to feel it. I should be able to feel the cord that I've just connected to my robot arm. These are things that we need. We need this kind of bidirectional interface. All right? So that's the motivation for this particular section. And here, This is again, you have many signals coming from the human body and many signals coming and going from the robot limb. Another example, many of you have probably seen movies along this line, but why not match signal spaces directly from the human brain to a synthetic body? I mean, that makes sense, right? If you can actually take all those signals and control a completely different body, or maybe you're a brain in a vat. Maybe you've been uploaded into a computer. How do you control your synthetic body with all of those signals that your digital or biological brain in the vat is generating? There's some good books about this too. I'm sure Kim's recommended many of them already. But even more, how do you connect it to anything? This is the big problem. How do you connect signals, many signals, to the rest of the world, the datasphere, the internet? How would you go about matching that signal space? That's a challenging problem, a challenging case of a dense and interesting data stream, sensory motor stream on one side of an interface, and a dense and interesting sensory motor stream on the other side of an interface. Okay, your key idea for this section is that there's often a very challenging disparity between the number of signals and also the nature of the signals, what kind of signals they are and what they convey on both sides of an interface. And just as a tag on to this key point, that as our technology gets more advanced, as our physical robotic systems and our sensory systems get more complex, it's getting harder and harder for us to even understand the data coming from both sides of that interface. We can't really engineer a solution anymore. This goes back to some of the points from the last talk I gave. But we can't really engineer those connections to the same degree we could in the past. And increase the complexity of those signal spaces another order of magnitude, and I'm going to hazard to say that is absolutely no way which we can go about making this link between dense and complex signal spaces. We need machine intelligence to do it for us. And that's the key idea that I really hope you'll take home, is that machine intelligence can start to build that bridge between, let's say, the complex signal space coming in and out of a human mind and the rest of this crazy, impossible, wild digital world. This is the link. The machine intelligence is making that bridge. And I'm going to show you some examples now of how that bridge might be formed. That's good? Is everyone tracking? Good. Okay, let's move on. So, in particular, you've noticed I divide things down usually into threes, and we're going to do that again today. Put the limb to bed again. We're going to look at 3 areas for augmentation and assistance. And I'm going to talk loosely. I'm not going to specify whether it's augmentation or assistance. We're going to talk in general about areas where we might want to use machines and machine intelligence to either replace, restore, or extend human function. And one that we talked about earlier is sensation, or perceiving the world. Another is actuation, or influencing the world. And the last is information processing, or understanding the world. So these are areas where we might want to augment or assist a human being using machine intelligence and machines. But this might remind you a little bit of last lecture, where we talked about what might a machine learning system or a machine intelligence system wish to learn. One is prediction, another is control, another is representation. All right? So keep these in mind, and we're going to sort of step forward and look particularly at control. Control has elements of all of these, and so we're going to look at control as our key example for this particular exploration of assistance and augmentation. So the first is, who remembers learning using labeled examples? Yeah? Okay, good. Do you remember that I showed you a bunch of pictures? I think it was like Iceland, Argentina, and then we had Japan as well. And I was showing how I asked you where this image came from, and then you give me an answer, say Argentina or Iceland, and then the system will learn based on the true answer. So you say Iceland, and it was Iceland, the system will make a match between that. You say Argentina, it was Iceland, the learning system will change its internal structure such that it's more likely to give the right answer next time. So this is our quick refresher. And here let's look specifically at recording. We're going to talk again about taking that saw, cutting open a little hole in the brain, and putting electrodes in. Oh, it's a very special time. The arm has just told me something. So the arm has just told me that it's gotten very, very warm. So these aren't the strongest servos in the world, and at a certain point, the arm is going to get effectively tired. It's going to heat up to the point where it doesn't want to keep going. And so what just happened is it actually gave me a series of vibrations on my arm to tell me, you know what, I'm getting tired, and in particular, this joint is getting tired. So you notice I've had its elbow holding up, it's been holding its arm up for a little while. Well, its elbow is getting tired, so I'm going to put it to bed right now. I'm just going to unplug it to let it cool down. And this will give it essentially some time to cool off. But that was an interesting example. I'm glad that actually just popped up, because it was an example of the system doing something, knowing something, and then telling me what it knows. There's no way, except if I would actually go around touching all of these motors, to find out how hot or how tired the motors are. But the system just communicated, yeah, you know what? I'm tired, put me to bed for a little while. So I did. Good. All right, back to learning using labeled examples. So here we have a recording from the human brain. Let's just assume, use your imagination, assume that we have some electrodes in the brain of a human, and we're recording signals. Let's say we're even recording from the motor cortex. You know, we've spiked right into the area that's usually responsible for actuating, for causing motion, and for thinking about motions. So, and we want to connect those signals. Let's say we record, I don't know, 20 or 30 signals, and we want to use those to control 3 different joints of a robot arm, kind of like the ones I have here. Maybe the shoulder joint, the elbow joint, and the wrist joint or the hand joint. All right, so we want to be able to control a robot limb. So, learning using labeled examples, one example of this is if we say, okay, let's put a learning system in between the human and the robot limb. So we're putting a machine intelligence system, a learning system in between those two. And we actually say to the person who's got the electrodes in their brain, think about moving your wrist. All right? So we're saying, think about moving your wrist. Elicit some mental pattern. This pattern will be changing and variable and wild and complex. But think about moving your wrist. And you can see, just on the slide here, I've indicated with gray circles that maybe some of those electrodes are going to spike. You're going to start to see more increased activity in certain regions of the brain when that person is thinking about moving their wrist. Again, this is an exaggerated example. But now what you might say is, okay, so learning system, this pattern is associated with moving the wrist. All right? So you've given it a label. You've said, the person is generating a pattern for you. It's a complex pattern. I don't know what this pattern means, but I do know that the end goal of this pattern is to actually move the wrist actuators. Say, learning system, whenever you see this pattern, or even a pattern similar to this one, this means you should be moving the wrist of the robot limb. All right, so then next time this system actually sees that pattern, it'll actuate the wrist of the robot. All right, and you can think of a similar thing for moving your elbow. You could now say, think about moving your elbow. So now the person with the brain-machine interface is actually thinking about flexing their elbow, or maybe they're thinking about the smell of burnt toast, or maybe they're thinking about rotating a cube. Maybe some of you guys have seen the emotive headsets and some of the other inexpensive EEG systems, where you actually sample some kind of electrical activity from the brain, and then by thinking about very, very different and discrete things, you can actuate some kind of assistive or robotic system. Some of you may have seen this. This is an example of that. Think about moving your elbow. You know, envision moving maybe the elbow you don't have anymore if you're a person with an amputation. And now you say to the system, when they think about this pattern, they want to move their elbow. Next time it sees that pattern, because it's learned that pattern, it'll actually move the elbow. Now, you also want to provide many, many examples. As you can imagine, the brain is also a volatile beast. It's something that's hard to put a saddle on and ride around, in that the signals will be changing and varying in really strange ways, and they may shift over time. They may even shift during a particular recording. And so you need to take many, many samples, and you need to let your system actually adapt to all the various patterns that might mean move your elbow. You remember last talk, we looked at Iceland. I showed you 2 pictures of Iceland. I told you that both of those pictures were Iceland, even though the pictures were actually pretty different. They were the same waterfall, but they were very, very different pictures. But they both were assigned to the label Iceland. Here, there's many patterns which may be almost indistinguishable from each other, or they may be very distinguishable from each other, but they all mean move this particular joint of the robot system. All right? Is everyone understanding this? They're tracking well? Good. Okay, so your key idea from this section is that you can learn from labeled examples, and you can do so especially when a domain is well known but very complex. You know you're recording from a particular region of the brain, but you don't know what those signals mean. You know you're sending this to a robot system, but you don't really know how to make that connection between all those strange signals from the brain and the different joints that you have access to in the robot. Sometimes in robotics, for those who are fans of robotics, sometimes you have a very well-known and well-defined model of your robot. a lot of commercial robots, you'll be able to have a simulator which almost performs like the real robot. You'll know the dynamics, the kinematics. You'll have a fully specified robot. Then you have robots like this. I hacked this thing together. The first iteration I hacked together on my kitchen floor with a hacksaw and some tubes of brass. And it took about 2 days of just sitting there sawing and building and bolting. I don't have a fully specified kinematic model for this or dynamic model for this system. I haven't tried, and I don't want one. Because in the end, much like a biological limb, the systems need to grow together. The systems need to be able to understand the limitations and the extent of each end of the human-machine interface. So there's many cases where you will have a well-defined model of your system, but there's many cases when you won't. And this is one example where machine learning is a good tool to have in your toolbox. Oh, and just a small point on that last slide is that often a lot of that learning from labeled examples can be done offline or in batch. You could say in a clinical session have someone come in and say, think about your elbow, and then think about your elbow again, and think about moving your wrist. Think about reaching for a cup. Think about scratching your head or taking on and off your glasses. And then you could take all of that data with the labels that you've provided and use that offline. Use that to train the machine intelligence system when it's not connected to the person. And then next time when you hook it up to the person, assuming their signals are more or less consistent the next time, which is a big assumption, the system should perform well. But often you need to recalibrate when you connect it up. And I'm happy to, during question session, discuss that a bit more because there's some really interesting and exciting ideas and also challenges with respect to whether or not you should actually retrain this kind of connection or let the connection continue to evolve over time. So we can talk about that later if you like. But let's move on to our next set of examples, which is learning to actuate through trial and error. Now, some of you would remember the example from the last talk where we looked at going to different locations and shooting photographs and then seeing how much money you make in each location, using that to decide where you might want to take your next set of photos. Same kind of example here, and same kind of setup. So we have a human brain, we've got electrodes, we're recording, and we have a robot system. And there's some kind of machine learning or machine intelligence system sitting between the two. In particular here, we're going to have one special kind, which is a reinforcement learning system. This means that the system receives signals. This could be signals from the brain and also the robot limb. And it also receives a special signal called reward. Reward is a single channel, a single signal, which tells it how good or bad it's doing at any given time. This is kind of like when, who has dogs? Who has puppies? Okay, a couple people have puppies. So when you're training a puppy, you can imagine that like the puppy does something correct, you try to teach it a trick, does something correctly, and you'll actually give it a treat. You'll say, okay, good job, you did this correctly. And if it does something bad, you might smack the table with a newspaper. Maybe it chewed on your walls or something. And you'll just be like, you'll express your disapproval that this wasn't good. And so by positive and negative reinforcement or corrective reinforcement, you can actually give feedback to a system. Now, we talked about this before, but I'm going to bring this point up one more time, is that this is kind of nice. You may not know how to achieve the task. You may not know the exact sequence of muscle actuations that that dog has to perform to sit or turn in a circle or stand up like this. But you know when it's achieved that. You know when it's sat or when it hasn't gone chasing off down the road after someone. You know when the correct behavior has occurred, but you may not know exactly how to get it to occur. So reward is one way to train a system to achieve behaviors or objectives or goals without knowing how you might go about achieving those goals. All right? So we can do the same kind of thing in a human-machine interface. And in fact, our group has shown some really interesting examples, and there's some folks down in the States. I think I've even recommended some papers to some of you on some of these particular examples of human-machine co-adaptation through reinforcement learning. And here, again, we might say something like, okay, I want you to think about moving your wrist. Again, the brain generates a pattern. Different signals are on or off, different wires, different data points are active in different ways. And now, the learner actually tries something. It learns through trial and error. Maybe it tries to move the elbow. It says, you know, maybe when I see this, maybe you mean I should move my elbow. Should I move my elbow? Maybe I'll try it. I'm going to move my elbow. And then you're like, no. You know what? No, I really didn't want you to move the elbow. In fact, you just like punched me in the face, or you like smacked me in the thigh and gave me a Charlie horse. I really didn't want you to move the elbow. So in this particular setting, this is a bad thing to do. It maybe doesn't mean don't move your elbow ever in response to this pattern, but it may mean in this situation, this is not a good thing to do. The outcome was poor, and you're going to get a poor outcome too. So now the learning system may say, okay, I just got some corrective reinforcement. I got some feedback about what was going on. This feedback could be manual, it could be automatically extracted from the human-machine interface, but there's some feedback which says that was a bad action. So that learning system will now, knowing what action it took and what signals it is currently seeing, will update its internal structure based on that feedback. It'll be less likely to pick the elbow action next time it sees that particular train of signals. It may try something different. It may pick action too. It's, okay, I think you really wanted wrist when you saw these signals. Maybe it was wrist. I think you want wrist. Your puppy also kind of does this. It's like, do you want me to sit up? Do you want maybe shake a paw? Do you want me to shake a paw? I'll sit. I know you have treats somewhere. Maybe you want me to sit. The learning system is doing the same kind of thing. And so maybe it tries to actuate the wrist. And here it gets a +10. You're like, yeah, that's exactly what I want. In this setting, maybe I'm going to shake someone's hand with my, let's say with my biological limb. I'm going to shake someone's hand, and I want you to actuate the wrist to be in the right place. In this situation, that was a good action to take. So you give positive feedback, positive reinforcement that that was the correct action. And again, the system will update its internal structure such that it's more likely to take that particular action again in that setting. It sort of has a way of telling how good or bad it is to be in any part of the world or to take any kind of action in any part of the world, and uses that to change its policy, change how it interacts with the world and how it outputs actions or controls. Okay? Good. So the key idea here is that learning through trial and error can actually be really effective. And it can be effective in domains where you don't really know what's going on. Poorly specified domains, or domains where it's clear what goal you're trying to achieve, but you might not know how to get there. There's examples from artificial limbs we can talk about later as well. But what's nice about this approach and the algorithms that support it, the computational infrastructure and that's been built up around this, is that it can often be done in real time. So this kind of learning can be done while the person is interacting with the system. For instance, while I'm interacting with this particular limb system. All right? So we're going to look at one last example, and we're going to sort of wrap up. Last example is improving our actuation. So let's say we do have some kind of mapping. We already have a mapping between the human and their robot device or their assistive device, or their device of any kind, a machine intelligence system. So normally, we would have something like I'm showing in this slide. You'll have let's say a system that involves, let's say, a robot hand and the human using it. So you have some kind of controller. Showing a controller here up in the top side here, you can see the controller. We have some kind of controller, and that controller usually has parameters, and it has some way of mapping, of taking in information about the user and their device, and then spitting out actions to control that, let's say, that robot hand. All right? So what we're going to talk about in this very brief section is how you can actually maintain and use knowledge, how a learning system can build up facts about its world, and how that might be able to improve that mapping or improve those parameters. Okay, so here what you see is there's state information, goes through a mapping, and spits out control actions. And as we saw earlier with our learning from labeled examples or the learning through trial and error, often that mapping is in the form of predictions or some kind of learned system. So here, in conventional controllers or even many pattern recognition or pattern analysis systems, the predictions or the knowledge is all bundled up. It's rolled in. It's baked into the cake or stirred into the soup of that controller. So the controller embodies that knowledge, but it's not explicit. It's essentially, it's implicit. It's inside the controller. So an alternate approach is to actually pull some of that knowledge out. Not to say to remove it from the controller, but to allow a system, allow machine intelligence to actually build up facts or information or a predictive model of the world, to build up a whole vast sea of predictions about the user and their device while the controller is doing its regular operations. So there's this stream of information coming from the user of the device and the device itself, from the human and their machine intelligence or their assistive device, and you can have machine learning build up facts about that stream of data, about that interface. All right? So what do you do with the facts? Well, what would you normally do with facts? Well, you can actually use some of those facts. Use those tiny minutiae, that information about the world, the learned details about the world. You can use that to change the parameters. You can actually tweak the setting. Maybe when my system gets fatigued, maybe when this system gets fatigued or I get fatigued as a user, the system will just start to use that knowledge, its prediction about my fatigue, to adapt or twiddle one of the knobs in the controller so that the controller maybe amplifies my signals more, so I have to work not quite as hard to make the same reaction. Or change the way that the system actually actuates such that it doesn't get tired and go to bed. Right? So that's one thing we could do. Another is we could actually use predictions as information to the controller. This would be really smart. Normally, and almost exclusively in most controllers, the controller, or the thing that's creating that link between all this state information and the actions that need to be given to a robot system, almost always the controller sees what's happening right now. And maybe sees a little bit about what's happened in the past, but very rarely does it see what's happening in the future. So by building up facts, by building up predictions or forecasts, a machine can actually start to say, all right, I can guess what's going to happen in the future and use that to change how I'm acting, change how I'm interacting with the world. So this is a neat step forward. By building an explicit model of predictions, an explicit predictive model of the world, or a reservoir of facts, the system can say, all right, every time I've been in this situation, these kinds of things have happened in the future. And then feed that information into the controller, its conventional controller, as just normal inputs. Or, you can even go a step further. You could have the conventional controller controlling, say, 2 degrees of freedom. In this system here, let's see if it's actually if it's awake enough to come back to life for us. If it is, I'll spark it back up and I can give you an example. Good. And there we go. Good. So we're back online. So right now, I'm controlling 2 degrees of freedom. I'm controlling up and down and left and right. All right? So what's cool is that if you can take a predictive model of the world, you might be able to say, all right, I'm going to control only 2 things. I'm going to control 2 joints, but machine intelligence, I want you to directly control the other joints. So when I'm doing a task, I'm going to give you the gross motor movements, and I want you to take care of the details. If I'm grabbing for something, I want you to figure out exactly how to grab this object using this predictive model, using this rich, structured version of the world. I want you to actually sculpt some of these other joints for me. Or I'm reaching for the table, I want you to rotate my wrist such that when my hand gets to the right place, it's in the right orientation to pick up a pen. So this is the kind of thing that we can start to build up using a predictive model. So again, we can look at tweaking parameters. We can use facts about the world to tweak parameters. We can use it to change the mapping, how we take this information from my body and use it to control the robot system. And we can use it to directly control things that we don't currently control, to make our interface or our interactions more streamlined or more seamless. All right? So these are things you could possibly do. And what's really neat is that because of the way we can learn these facts, we can have it learning all the time. It's not just learning for a little while, then boiling that down into some kind of magical ball of machine learning. You can have the learning happening all the time, maintaining and updating those facts, such that as I go about interacting with my world, these facts, these predictions, these anticipations become more and more precise over time. The system can get better at doing these things in real time during ongoing learning. That's kind of neat. So your key idea here is that finding structure in the data, and in particular, maintaining this knowledge, building up and actually capturing this rich reservoir of facts, and then making sure that they're correct, checking to make sure that they match with your current experience. This can be really useful, and it can be very useful, especially when your domain is changeable or non-stationary. And I would argue that a lot of our brain-body-machine interfaces are changeable and non-stationary. All right? And so here is just one example. Now, many of you have maybe seen this video as well. It's from the wonderful folks down at University of Pittsburgh, and this is looking at direct brain-computer interaction. Here, Jan here has actual connections directly into her brain, and she's using this to control a modular prosthetic limb, that amazing, highly dexterous robot limb I talked about earlier. She's using her thoughts to control this robot limb so that she's actually feeding herself a chocolate bar. That's pretty wild. And that uses these kind of technologies to mediate, modulate, and enable an interface, a way to connect all those brain signals to the commands of that robot arm such that she can purposefully and willfully move objects in the world and perform daily functions. This is really miraculous. And this is the kind of thing that machine intelligence can enable. I want you to keep this as your motivating example, as your reason why we should think about machine intelligence and why we should think about it specifically in terms of assistive and augmentative technologies. Right? So there are some open questions, right? And one is, well, looking at my system here, when signals and information is really plentiful, how do we go about using those signals and gaining function without losing function? So right now, I'm controlling this arm using a joystick. I'm not using my fingers for anything else. I have to waste a whole hand, more or less. I mean, I can still do things with my pinky, but I have to waste a whole hand to control these 4 degrees of freedom. So I get a little bit, but I give a lot. And this is a common setting. How would we go about thinking about a system? How would we go about generating an interface that allows me to control this robot arm without sacrificing degrees of freedom, without sacrificing function that I already have? I mean, you could think, well, you know what, we could just stick electrodes to your butt cheeks, one on each butt cheek, and you can use that by contracting and flexing. Well, I'm still losing use of my gluteus maximus, medius, and minimus. So how do you minimize the loss of function while maximizing the extension that you gain through your assistive system? How do you do that? That's a hard question. And I have some other examples here. I mean, how would I control a prehensile tail? This is something my student Adam Parker and I talk about. How do you control a prehensile tail? This is even more it can wrap in many different ways. How would you do that naturally without really having to work at it, without having to put all your cognitive load on that tail? Another is, how would you control a pair of wings? I think many of you probably thought of that. If I had wings, how would I flap? Would I flex my shoulders like this? I don't know. But birds do it. Other animals do it. This is a fairly natural thing for certain creatures. So would it require some kind of adaptive interface between the human and the device? Probably. Probably has to grow together. Another is that when information and signals are scarce, how do you extract the most? How do you wring out the most from that limited information? So, I mean, how would I fly an airplane with one hand? This is actually something pilots usually do. I mean, they only have so many parts on their body. How do you go about flying an airplane? There's all sorts of switches. There's flick things all over the cockpit. There's little knobs. There's buttons. I mean, how do you control a very complex system with a limited number of channels? Or how would I drive a race car using only a single button? It's not just about giving signals too. It's if you only have a limited channel of spitting information back, how do you give back all that information from the airplane or the race car, the feel of the tires on the road? How do you communicate that back to the person using the system? That's a hard challenge too. And these are things that I believe machine intelligence can help. Because one possible solution, and I'm going to put this forward to you, and I think that as the years to come we'll explore this more fully and we'll see some great promise here, is that maintaining and using knowledge, and here I'm going to talk about representation, prediction, and control in a purposeful way, is a way to solve those open questions. It's a way to attack them in a very strong way. And it's a way to enable us to do things we could never do before. Or, boiled down even further, machine intelligence is going to enable an entire new generation of assistive and augmentative devices. It'll enable us to restore function that we may have lost. It'll enable us to take our innate functions, our natural physical, cognitive, and perceptual abilities, and extend them to the point that we can only today imagine. It'll really take us to a realm where human intelligence is being augmented and extended into some strange hybrid between humans and machines. And we're already getting to that point. So machine intelligence opens the door for technologies that we cannot even think about today, and some that we can and really look forward to, like a third arm. So, let's go back to our learning objectives. We have exactly 2 minutes and 6 seconds left, so let's look at our learning objectives. So, hopefully, you can all now define augmentation and assistance in terms of technologies and devices. Is that correct? Good. Okay, good. And hopefully you can also understand the 3 key interface challenges. So one might be taking a limited number of signals and sort of expanding them out to a very complex system. Another is taking a complex system and focusing them down to 1 or 2 different control degrees of freedom. Another is matching. The general case, remember the general case is matching. Taking a wild, rich set of signals and turning that into something that can connect to another rich, wild set of signals. And also, you should be able to state why machine intelligence is actually important to that kind of matching process, and more specifically, to human-machine interaction. The extended learning objectives here is one, you might want to understand what abilities machine intelligence can enable. So hopefully, You actually do. Hopefully you can imagine what you might want to enable with machine intelligence. Maybe it's extended sensation. Maybe it's better actuation or different actuation. Or maybe it's restoring lost information processing. Maybe it's finding ways to replace functions of the brain that have been damaged through a stroke or through an actual physical injury. So these are the things you might want. Sensation, might want to change your actuation or enable better actuation, or information processing. And we looked at 2 examples of how machine intelligence might enable that. We learned through labeled examples, and we looked at also through learning through trial and error. And then we talked briefly about building up and maintaining knowledge as a way of adapting this kind of connection. And finally, we talked about a lot of different examples of how machine intelligence might be used to assist and augment humans doing the functions of daily lives and functions that may soon become part of their daily lives. So with that, I think we are exactly at time right now. So we are now open for questions. Thank you again.
So, you know, I was struck as I listened to you present here. We often think of this as something rather abstract. In other words, what you were talking about doesn't actually have anything to do with anything that we're doing right now. But that is actually not the case, because if you think of the YouTube videos from this course and the table of contents from those and so on, and getting meaningful data from those, there are a lot of assumptions that we make that are similar to what you're talking about here. You kind of train the system by getting more and more people to watch the videos, and you assume the data is more valid if 1,000 or 10,000 people have watched them than 2 or 3. But you know, that's not necessarily so. You can imagine that there might be just a few people who go in and watch and behave in a highly meaningful way that would indicate to you what the true high point of the lecture is. And if you then get several million people, you would lose that data because they would be interested in some other high point. And something that's intrigued me in the last day, when you think of very small numbers, like if you think of a robotic assist device that's very expensive, so few people have it, and you're trying to get data from this, and you would say, well, with low numbers, you can't get any data. If you look at the site poetry.com, there are millions of people accessing that site. I think 7 million, because a lot of people think of themselves as poets. They're not really poets, but they think that they are. And you would think that the data there is not very valuable because a lot of the poems are only reviewed by 1 or 2 people and then given a score. Some are reviewed by up to 1,000 people. Well, you might say, well, that's valid. But actually, if one person goes in and gives a poem the highest possible score of a 5, then there are millions of people who have the opportunity to go in and provide a lower score. They don't think it should be a 5. So the people over time who maintain the score of 5 for a poem based on one reading, that's actually lots of people looking at that scenario, you know, and deciding not to go in and give it a 1 or 2. So there are many counterintuitive things about this, but I would say that there are real parallels and similar considerations between what you've been talking about today and the way that we will later analyze the video from this lecture. So in that sense, it's not abstract at all. It's directly relevant to the lives of everybody in this room.
Yeah.
So any
actually, I'll just respond to that, actually, Kim.
Yeah.
So one point you addressed is the sort of the tyranny of the data masses.
Yeah.
Essentially, that you at a certain point you might start to get like noise creeping up on what you consider your signal. In terms of this course, I think specifically about, well, what if you have web spiders going in and completely polluting, and maybe they all watch just the first section of the video, or maybe there's even video crawling web spiders, and that would totally throw off statistics. So the question then is, well, is that really noise? And many of you may have heard me say this before, but I don't believe in noise. I don't think there is noise. I think there's a signal that we don't understand or our systems don't understand. So this goes back to the ideas of representation and how do you actually start to segment out that rich stream of data coming in. So I would say that especially with respect to the assistive devices, that it's us better understanding the signal we have. And same for the way that this data will be analyzed in the course is that some of the current metrics or the current measures are perhaps not as sensitive. The representation perhaps is not rich enough to capture the key information. So when you do have millions of viewers coming in, well, you can start to see some kind of trends there, but there's a lot of information hidden there. You can pull out the different cases and different settings, and that's important as well. It goes also a little bit back towards clustering. We talked about unsupervised clustering or essentially learning from the structure of the data last talk. And same kind of thing. Can you pull out that small population which was really interested in viewing this particular part of the talk, and that's all they really hammered in on, and it related to this other talk that they saw? How do you pull out all of that information from the data you have available, as opposed to getting it lost in what you consider a sea of noise? And the same is also true, I think, for instance, for some of the online writing communities as well, that you pointed out. And also to respond to your point about poets, if someone thinks they're a poet and they write poetry, they're probably a poet. That's the inclusive view is often the best view, or at least the most successful view. So, but let's open to questions.
Yeah. Leonard Cohen says poetry is not a profession, it's a verdict. So it's a verdict somebody makes.
I have a question on topic for signals. I'm curious how Zach is able to use his leg when his body chemistry changes. So when he gets scared and gets a shot of adrenaline, does his leg work the same?
Yeah, in terms of the adrenaline, this is something I don't actually know. The one thing to think about here, this will hopefully clarify, and also maybe even give you the answer to your question, is that the way this surgery works is kind of like rewiring a house. Okay? So you have wires going through your house to light switches and things. So now imagine that one of your light switches stops working, right? Toggle it, nothing happens. The switch is broken. The leg is lost. You take the wires that go to that switch, and then you reroute them to another switch in the house. All right? Now you toggle the switch, and the same light goes on. So think of it like that. What's happening is that there's the pathways from the brain down through the motor nerves, going down to Zach's lower limb, or in the case of the people with amputations we work with here in Alberta, to their upper limb. They've lost upper limbs, and we perform this surgery. And so what's neat here is that now when, let's say Zach thinks about moving his leg, the same part of the brain fires. Maybe there's small changes due to plasticity, but the same part of the brain more or less fires. Those signals go down the same motor pathways they would have normally gone down, but now instead of terminating in a muscle that's no longer there, they terminate in a muscle that does exist. The surgeons have gone in and reattached the nerve to a muscle that still exists. Maybe, like in the upper limb, let's talk about upper limb, your bicep has two heads. Why not snip the nerves from one side? You're not using it anyway, you don't have an elbow anymore. Why not snip the nerves from one side, rewire the nerves that would have gone to, say, flexing my wrist into that bicep head, give it 4 to 6 months to regrow. Now when you think about flexing your wrist or closing your hand, half of your bicep contracts. Same kind of thing for the lower limb. So now, really, it's the same pathway from the brain. So one would hope that when there's a response, like an adrenaline response that causes the body to move in different ways, taking out the adrenaline system in general, you'd expect it to respond more or less the same way, given the actual motor pathways that you've managed to reroute. And it works the other direction too. Not in Zach's case, I don't believe, but in the case of some of the other folks from down at the Rehab Institute of Chicago, and also some of our fine patients here in Alberta at the Glen Rose and through U of A Faculty of Medicine, Rehabilitation Medicine, and various other divisions and departments across the university. Sensation is coming back. So our team is looking at all sorts of cool things, but one of them is being able to give someone the sense of touch. So when their robot arm touches something, they feel it in the hand they no longer have. And when they move their arm to, this is something Jackie Hebert and some of her close colleagues are working on right now, we're working on this, is kinesthesia, knowing where a robot arm is in space intuitively. So these are really cool. These are things that are happening right here at the University of Alberta and in other centers across the world for restoring both motor function and sensation and having them work more or less the way that they would have in the biological system. That's a long-winded answer to your question, but hopefully it sort of hits in on a couple of the points you were looking at.
Gets close.
Yeah, so I think you just mentioned, I was going to ask you about proprioception, but I think you just went over all of that. So my question is about subconscious limb control. So oftentimes you just have sort of like a, reflexive movement based on, something comes whizzing at you and you kind of dodge out of the way. So for these prosthetic limbs, the users have to really think about the motion. They can't just intuitively sort of move their hand and, okay.
Yeah. So this is currently, yes, there's some, I'll use this as sort of a segue into some of the key barriers to conventional artificial limbs. One of them is that they're ridiculously hard to control for the most part, or they're challenging to control. They require cognitive load or cognitive effort on the part of the user, partly because they can't feel, partly because they don't have these reflexive actions. They don't give good feedback back to the user, and in general, they don't, they also have a lack of function. They don't have all the density of functions that we would like, all the bits and bulbs of a native limb. So to go to your question, this is one area I'm particularly passionate about, where a lot of my research is focused, is building in those kind of reflexive actions. And so we actually published a paper earlier this summer on the use of predictions. Remember the slides I showed at the end where I showed the blue boxes and the use of a predictive model of the world to actuate some subset of the joints? That's the kind of case we can actually get towards with using predictions. We can actually build in these reflex actions. So we can start to say, okay, system, I'm still controlling what I'm normally controlling, but when you see these kind of situations, and when you predict these things, there's reflex actions that can be built in for safety of both the device and the user. So this is kind of neat. It's almost what happens in the actual spine, right? A lot of reflexes sort of come downstream. It's not, going all the way to the prefrontal cortex or something. There's a lot of loops, a lot of motor patterns which are encoded right in the bits and bulbs of the spine. And so what's nice here is that we're doing the same kind of thing with our machine intelligence. We're essentially building like a little mini spine that can deal with some of these reflex loops, some of these predictions and forecasts and anticipations, maybe throw in a bit of cerebellum too. But essentially we're looking at ways to build in these reflex actions so that it does work like that. Because you're right now it takes a lot of concentration, especially for harder tasks, and because you don't have this feedback. You don't have appropriate, you don't know where your limit is in space. I don't know, like, if I close my eyes, where's the end of the X arm? Okay, it's right here. But I don't know that intuitively, and I should. So, does that answer your question?
Yeah. And I've got one more question too, but it's
Sure.
a little bit more philosophical, I guess. So I was thinking, so you're talking about machine intelligence and learning and how maybe you can use it to tackle a complex problem that you wouldn't normally be able to. So I was thinking about something like economic policies, because it seems like everybody's got an opinion and nobody seems to ever get it right, and it's always fluctuating. So maybe, let's say you design a machine that can take in all the massive amounts of transactions that occur all across the world and spit out, something meaningful and tell you, okay, you guys need to invest here. So I guess one of the things I was wondering is that if you have a machine that's really making these conclusions that you wouldn't normally be able to do, and then you just sort of have to trust the machine, is there anything wrong with sort of, I guess, giving that amount of control? I guess it's sort of like the first time that humans wouldn't really be making decisions for themselves. They're letting somebody else do the decisions for them. Is there anything wrong with that, potentially?
So that's an excellent point. It hits on a lot of aspects of our lives. So, for instance, flying airplanes. A lot of times airplanes are able to do a little bit of their own piloting. We have to trust that. But that's not the right answer. That's not the answer I'm going to give you. The answer I'll give you is that transparency is important. And what do I mean by transparency? By transparency, I mean making the internal workings of the learning system more apparent to those that are interacting with it. So again, I talked about interfaces of this variety, but the interface between humans and their financial environment is another great example. There are all these examples, and you hit on a very good one where machine intelligence is being used as much as possible because people like money and they want to make more of it. So And yeah, in some cases, like policy making, forecasting, stock markets, it's good if you can have a perfect oracle. You walk up to Delphi, you light some incense or something, and the oracle sways around a bit and gives you an answer, and you don't know why they gave you that answer, and if you ask them, they'll banish you and say never come back again. So that's all well and good, and maybe you get good predictions, but it's even better if you know the why. And I think that's something that especially some of the more modern machine intelligence techniques are getting better and better at doing, is providing why. Providing all of the, essentially, all of the detailed information about the world that goes into those decisions as well. Certain things like artificial neural networks are kind of, at least in the classical sense, are more like those black boxes, where you have this wild network of nodes that are connected by weights, and you have to train that up. In the end, you give it inputs, and it gives you an output. You're not really sure why. And you can sort of go in and do digital neuroscience just to check and fiddle around, but it's harder to know. If you have a system, say, building up a predictive model of facts, I'm going back to the facts example, you can query any of those individual facts. You can start to see more about what it's learned. So this is not a comprehensive answer, and I don't actually know the right answer of how to best get that transparency which enables trust, because it does take a lot of trust. If I were to say, you know, put all of my trust that this thing would be doing the right thing all the time, if I was going to trust it to help me drive a car, I'd have to really trust that when I'm putting in inputs, it's giving the right outputs. And trust is one of the central issues. So transparency is one issue I'll give you, or one answer I'll give you, but is it the right answer? I don't know. I don't know how to implement transparency in a flawless way either. But that's, I think, the right direction.
Yeah, no, I think that's a good answer. Thanks.
So the stock market is already in the circumstance that you described, that there's computerized trading. Doesn't matter how transparent it is, it's so fast that we couldn't possibly follow it. So the destiny of all of us is already kind of in the hands of machines in that sense, and there's starting to be a science about that. There's an article in the journal Nature about the little tiny crashes that you see. I mean, you can hardly detect what they are, but it's sort of, an imperfection in the machines doing the trading, but then they, recover and keep. So they're becoming peculiar patterns there that seem to be working out okay, but that would never ever occur if you had human beings doing the trading.
Yeah.
So this is not a future scenario. This is going on right now. It's already happening.
It very much is, and that really hits back to the need for adaptation and change and robustness. This is tightly coupled with the idea of robustness and actually trust as well. You want to trust that when something goes wrong, which it will always go wrong. It's not even wrong, it's that it goes differently. And you have to trust that your system will be able to handle those differences. I actually think to the massively distributed web searching. Let's look at what Google does. They have made massive clusters of computers, right? And a single search is split up and given to all these different computers. And you know what? Some of those computers die midway through the operation. They literally die. That computer will go offline. It'll have lived out its useful lifespan. But the system's able to essentially shuffle around the information such that your search still comes back and gives you the answer in like microseconds. And this is also part of that robustness and change. The system does die. There are glitches. You get strange cycles showing up that you wouldn't get if you had a single person looking through a filing cabinet to find out the answer to that query you just put into the Google search engine. But it's a different ecosystem. An ecosystem is maybe a digital ecosystem where things do change and there are novel cycles. But in the end, hopefully, if everything is moving forward, those cycles are still functional and still effective, and we can still trust them, going back to the earlier question.
Yeah, so just summarizing, machines are enhancing our lives, but it's a bit scary that we have to trust them to do a lot of things we can't possibly understand. So, okay, well, thank you very much. We're out of time. Thanks for a great teaching session.
Thank you very much.